but maybe not. We'll see. Anyway, all right, so to load dills, you can't just load a dill and run it. It doesn't do anything by itself. It has to have some program launch it, and then that program has to run dill main to initialize the dill so you can use it. So let me just show you this. Let's use OllyDbg and open C Windows System32 WS2 underscore whatever dot dill. So it should be in my list. Right here it is. So C Windows System32 WS2 underscore 32.dill, one of the main Microsoft libraries. So when I go to load it, it tells me, in the first place, I'm about to kill that game. Is that okay? And I say, sure, go ahead and kill the game. Now there's another box that popped up the first time I did this, which warned me that I can't load dills directly, so I was going to launch loaddll. There is a program, loaddll.exe, that you can just use to load a dill. So that's what it did. It actually loaded that and then loaded the dill. So now ws232.dill is here. Now, obviously, one of the things you want to do with dill is see the exports. Dill export in many ways in. You could run this function or that function, and you're loading the dill because you want to do something with those functions. So you hit View. Actually, what am I not seeing what I'm looking for? Oh, debug, call dill export. Debug, call dill exports. There we are. And you get nothing. You get paused entry point of debug dill. You just get a blinking light. You don't get a damn thing. Because it can't do that because it hasn't run dill main. And dill main is what sets up those exports. And on top of that, you can't fix it now either. What you have to do is reload it. So reload it, again, killing the existing process, and now you have to run it. This is going to run dill main. And now you can debug, call dill exports, and you'll see the exported functions. Now here they are. All these functions are in this library. A lot of them. That's the point of these things. And so, and you can now play with these functions. If I want to see what this accept function is, for example, I could set it up here. Now this function has 3 arguments. And I could just put values in here for the arguments and then execute it to see what it does. Or I could look in the disassembler to see what it looks like. If I do that, and then close this window, I'm now going to see that function in the disassembler. It looks like it sure doesn't do much. The whole thing is just maybe 10 machine average instructions. So let's take one where I know what it does, which is the recommended one from the book, which is N2HL. This converts a number from network order to host byte order. So it just takes one word of 4 bytes and reverses their order. That's a very simple function. So let's play with N2HL. So it is debug, call dill export, and now you have this list of things, and in that list you find N2HL. As usual, it sorts the lowercase and capital letters differently, and it doesn't even make a lot of sense. Maybe it's not, maybe Windows it's that they're the same. Anyway, N2HL is here. Okay, this has one parameter that goes in, so you can run it. So if I put in, let me just follow my step, okay, 7F0001 for 127.0.0.1. That is a network byte order. That's the way it's actually set over the wire. If you grab it in Wireshark, the high order byte goes first, 7F000001. So that's a loopback address. Now if I run it down here with call, I have to shrink this down to get my mouse to move. Okay, call, it runs, and when it's done, you know, it says done down here, the answer comes out in EAX, which is 0010007F. The bytes are now reversed. That's all, no big deal, but that's how you can run a routine. Now, if you load OllyDbg version 2 and try to do this, the N2HL library is not even there, which is just appalling. They can't even find the exports in the PE header and show them to you. That's how useless it is. Anyway, so that's the game there, and this is how you can run a function if you want to see one function go. All right, and here's OllyDbg version 2. It's not there. N2HL is gone. It's the damnedest thing. So now you can play with tracing, which is pretty interesting stuff. If you are in the middle of some program and you don't understand where you are anymore, which happens a lot, then you would like to find out how you got here, and there are various kinds of trace. You can do a back trace, a call stack trace, or a run trace. And these are all very powerful techniques, although I must say when I was new, I hardly used them at all. I'm using them a little more now. A standard backtrace is just like the back button in your browser. For example, here I am someplace in here. I should be able to do one from here. Let's just try, what is it, backspace? Minus. Let's see what minus does. In this case, perhaps nothing. Yeah, but we'll have a better example coming up. Normally, if you run through instructions, you can hit minus, and it will show you the previous instruction that was run, but it will not load all the register values and everything. It just shows you where did I come from. Plus would take you forward, minus will take you back to where you were. That's a standard backtrace just to see what was before this instruction. Now a call stack trace will show you the execution path to a function. And let me just load a simple function like the easy CTF here again. This is the thing that just plays a little game and all fits in one line. So right now, I'm right at the start of the program, haven't done anything, and if I view the stack trace, which I'm call stack. Okay, I came from the kernel, which is Windows, and I jumped into main. That's what this is. This is the return address to go back to Windows when I terminate the function. Now if I go forward some, let's use F8 again, and go down to call world, then I'm going to use F7 to go into that function. So now I'm going to move into this other location, calling put s. So F7 goes into there. Now if I view the call stack, there should be more stuff in it, and indeed there is. So here I am entering from the kernel into main. Here I am calling put s with this parameter, and now I'm inside there. So it showed how I started in this function, then I made this call to go into another function. And this is showing you the stack frames being stacked up. And remember, we looked at it before. You can also see the stack frames stacking up down here. Here they are. Here's the launch codes thing. That's what these are. Just showing you the stack frame of one module, and then you jump into another, and you have another stack frame. So now if I go forward some more with F7, we should see some more fun stuff happen. F7, F7, F7. This is going to call something else. So now I'm another layer down, and if I do view call stack, I now have even more things. So here I was in Windows, here I am in the routine, the main routine of the C program. Here it is calling something called puts, and here's puts calling something that just has an address, doesn't even have a name, some little piece of puts is implemented as a subroutine. And this is showing you how it piles up on the stack. Every time you call something, you make another stack frame with some room here, and one of the things stored on there is the return pointer. So when you return, it's going to look here to find the address to resume. These are the addresses you would target with an alpha null type buffer overflow exploit to take over the instruction of the machine when it returns from the stack frame. So that's what the stack frame does, and it's actually quite useful to know what calls led me here, especially when you're, for example, trying to debug a real program problem. My program crashed, which module called which module, what caused this? All right, so that's what I showed you here. All right, that's the entire main, step into puts, step into it again. All right, and by the way, when you return, of course, the stack gets shorter, of course. It pops things off the stack. All right, and here's a stack frame in a more complicated case. This is one of your lab exercises, Lab 0901, and as you can see, that's a pretty deep stack frame. Layer, 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 layer down. But that's how deep things get in more complicated pieces of code like real malware. All right, and the cool thing is a run trace. A run trace is like Microsoft Word undo. When I first found that, I was so happy. You could go and mess up your document. You could undo what seemed like 100 times. Totally play it back like reversing time, back to where I did the horrible thing, and try again. And you can do that in Olly, but it's not the default because, as you can imagine, it's super expensive in terms of time and memory to record everything that happens. So what you can do is you the run trace. And I did this for, this one. Let's do n2hl. This worked pretty well. So I'm going to load that n2hl library again. Win32, ws232.dill. Now I'm going to run it, debug, call dill export, find the n2hl thing. Oh, it's already remembered from before. I'm using n2hl. Good. So now I'm going to follow in disassembler and look at the joy of n2hl. And n2hl is as simple as that Windows game, as you would imagine. All it has to do is move 4 bytes in the opposite order, so how hard can that be? And it's this hard, it's about 15 instructions. So you can make these instructions. Remember, you hold down Shift and highlight them all. And then let me get it's run, trace, add selection. Okay, so it's right click, run trace, add selection. Now it develops a gray bar here telling me that now if I execute this stuff, Ollie is going to memorize everything that happens at every step. Every memory location that's written, every register that changes, it's going to keep a record of it all. So now if I step through this thing with like F7, yeah, it's going somewhere crazy. I should have probably set it up better. Let's just go back to here. Debug, call dill export. I should probably, good, I have a value. I should probably call it like this. And now it's done. So it has run through the whole thing. And now let me view it because somehow I've ended up somewhere else. I may have to just reload the whole thing depending on how much I've filed up. Oh, good, here we are. So now I've run through it. Once you have executed the code, that gray bar turns red. And now you can go back. And I think it is just minus to go back. So now if I hit minus, it goes back. Here's the return, here's that and that. And notice over here on the right, all the registers are changing and the red values are things that change. It's undoing these instructions, just like Microsoft Word. You can undo the instructions and then go forward and do them again, which is pretty awesome and expensive, and you don't want to highlight your whole program and do this. You want to do this for one routine where breakpoints and single stepping is not working and you really want to find out what gives. But still, it's pretty cool. All right. So, that's the game there. All right. So you can run it. Okay, so I did that. You've seen it. All right. And of course, you can do it in Lab 09. Here's the run trace again, showing you all the steps. It'll show you all the commands and everything. Remember, you can list them all here and go back and forth through a list of commands if you want to. All right. So you can trace into and trace over, which is another way to add more things without having to do add selection. Just like you can step into, you can trace into to extend a selection to cover more code. If you don't set breakpoints, though, it will try to trace the whole program because it'll trace into and keep going, waiting for a breakpoint, and then you'll probably have something too slow. All right, then there's debug for conditional debugging. This will trace until a condition hits. So you can specify some condition like the EIP being in some range up there and other things being true. Then you can have some kind of mathematical condition that will tell it when you're done tracing. So, you know, they thought of everything. This condition catches poison ivy shellcode because the way poison ivy works, remember that all your program starts at 400,000. Poison ivy allocates space below 400,000 and then puts the shellcode there. So this watches for EIP going into that space. And it will then trace the execution of the shellcode, but nothing else, which is pretty cool. Anyway, all right, a few eye flickers about that stuff. We just want to show all the subroutines that were used to reach your current location. All right, so I can quit at 25. All right, and that is the call stack, the series of calls that led here. Call a subroutine, call a subroutine, call a subroutine, and that is the range. You also see it graphically in the stack there, all of the stack frames, but the stack frames might be big with thousands of bytes of local variables. This shows you the name of each routine you passed through to get there and all the parameters that were passed to every routine so you can find out what caused a crash. All right. What kind of tracing is always available? Quit at 7 or 25, there it is. All right, you can always do backtrace, where you just the backspace, with just the minus, where you just move to see what instruction was executed before this instruction without setting all the registers. The other ones you have to prepare in advance by marking some region to keep track of it. Although, oh wait a minute now, I think I'm supposed because call stack trace is also, well, there's nobody answered that, but anyway, this is not a very intelligent question because call stack trace is also always available. And for future reference, I'm going to get rid of that one. But today, nobody voted in anyway, so we will continue with these sleazy questions. So, all right, which option might consume a lot of RAM? All right. I might have a problem grading this one too. I was afraid you would say that. Probably run trace and trace into both have this property. I think I'll settle for E being the smartest answer. Okay. That probably is the best answer. Not what the first thing that came to my mind, but it's true. Both of these can end up hogging up way too much memory. This one's probably even more dangerous because you don't control where it ends. All right. What feature saves every instruction and every change to registers? And I think changes to memory too. All right, that's the run trace. None of the else others do it, but the run trace does. All right, so now there's some more advanced stuff to talk about here, which is how you handle exceptions in OllyDbg. Now remember this, when OllyDbg hits an exception, like a CC, the first thing it does is pass that to Olly, which presents it to you. Now you can choose, if you're just put in a breakpoint and you broke, then this exception is not interesting in itself, it's a tool you're using to analyze the malware. But if it's an exception that you didn't put there with a breakpoint, then the program actually crashed somehow, and now you might care. So Olly will tell you the program stopped at this point, what do you want to do? You can pass that exception onto the program if you want to see what the program's exception handler will do, and you'll be doing this in the homework I'm working on. I haven't, well, we'll be doing this in the exploit development course, not this one. They're going to be doing SEH exploits, where you have to pass the exception back to the program so it'll hit the exception handler, which is how it works. But it's an issue. So that's why you have these choices. You can step into the exception, which means return control to the program and do one instruction, or F8 or F9, depending on how much of the program you want to run. F9 will just return to the program and run again. Anyway, those are options. In malware analysis, we're more likely to just ignore the exceptions because they probably just reflect bugs in code. However, it is possible that some exploits deliberately trigger exceptions because they've taken over the exception handler, and that's the case in the exploits we're developing in the exploit development class. All right, and then there's patching, which we did a little bit, where you're going to modify stuff. Like we knocked out a few things in that Windows thing, and that's the simplest case. You can just right-click binary edit, and you can change the contents. There's an option here to fill with zeros or fill with nops. That's one way to go. The other way to go, which I did there, was go to assemble, and then you type in assembly language instructions. Any way you like. Nop, of course, is what you use to skip instructions, so just nothing will happen. And that's, like I say, how you accomplish that thing in the previous iClicker where I said, what will skip over code without executing it? Well, it's not that normal, but this is what does it. Fill it with nops, and obviously won't execute that code anymore. You can save the patched code. It's actually pretty difficult to do. If you do a normal save from OllyDbg, you're going to save the debugging points, like breakpoints and stuff. But if you actually want to save a modified executable, you have to do this thing, copy executable, all modifications, save file, and so on. It's kind of cumbersome. All right, and if you want to analyze shellcode, you have shellcode on its own. Remember, this happens, like MSF Venom produces shellcode, or you get it somewhere. You'd have to load it somewhere in RAM and run it, even though it doesn't have the natural preambles and stuff that it needs to have. So here's how your book recommends doing it. Find the memory map and find an area of private memory, do a hex dump, and make sure you've got a region all full of zeros, and then you can change the permissions in Olly. You can give yourself full access to make it executable and writable, and then you can just highlight in and change the EIP to point to that shellcode. So this is one way to do it. There is a more common technique I've seen where you just write a C program that loads the shellcode and executes it, which is really pretty easy. You can do it in Python too. You just allocate some memory, put in the bytes, and then jump to the start of those bytes. By the way, in Python, it's in my 124 class, if you do it this way, you can slide any kind of malware past any antivirus. They don't seem to care. It was published in the book Violent Python about 4 years ago, and the author was horrified when I contacted him after 2 years and said, this still works. He said, you mean that still works? It still works. Anyway, I guess the real bad guys aren't doing enough real harm with this technique for the virus people to care, but if you make the slightest attempt to slide code past antivirus, you will discover how very, very weak it is. Antivirus is not like a fence, it's more like a curb that just stops you if you aren't trying at all. If you try at all, you sail right past it. Anyway, there are some assistance features. There's logs that will show you all the steps you took to get here. So if you forgot what you did, you can go back here. There you can have watches that will watch an expression. So I can be watching, for example, EIP and see all the value it has, or I can have some more complicated expression that I'm watching to see what will happen to it. You can label things just like you do in IDA. You can add your own comment labels to things to guide you through. And you can add plugins. I think it's Python based. I think OllyDbg is, but anyway, you can totally write plugins, and there's a community of people adding plugins to do all sorts of things. Here's a few I found, or maybe I don't know if I got it from the book or where. OllyDump will make it easy to dump the debug process to a PE file, so that would be handy for patching these Windows games. You can hide the debugger. OllyDbg from that means OllyDbg will somehow conceal from the code that it's running in a debugger. This is, there's virtual machine aware malware now, where it notices it's in a virtual machine and then acts different. And that's very easy because virtual machines have a different name for the network adapter and a different MAC address and a bunch of registry keys. So OllyDbg apparently has some cloaking feature that tries to prevent the malware from realizing it's in a debugger. You can run it from the command line, although I don't know why you don't just use WinDbg in that case. You can have bookmarks to bookmark memory locations as opposed to breakpoints, another way to label them, and so on. And you can also script debugging. So Immunity Debugger uses Python scripts and easy to use API. I guess OllyDbg doesn't. And so there's a bunch of scripts there, and they're just in Python. So they're easy to read and easy to modify. So you can automate debugging processes, and that would be cool for specialized cases. In this class, we're just going to do the very basic functions, but like I mentioned before, each one of these tools, OllyDbg and IDA Pro, are worth a whole class on their own. WinDbg, they'd be worth a whole book and a whole class on their own to really get into them. Anyway, let me stop the recording at this point and to see who won the iClickers. So it's 126, chapter 9b.